Center of gravity is going to be our new topic. We are going to be covering in mechanics. Okay, so we are going to start with weight, and then when we come to the center of gravity, then the center of mass, and then we'll see what happens. I'm going to use this as a reference when I'm explaining the things. So, we start with weight because you need to know what weight is before we come to the center of gravity. Okay, weight is the force of attraction of an object towards the earth. So if I have this as my body, always weight is acting like that. So this is the force of attraction towards the earth. So that's what we call weight. So always weight is always acting vertically downwards from the center up to the way you see it is always acting downwards. Then the center of gravity, this is the point through which the body's line of action of weight acts. So, you see, if the weight is acting in the middle, then at this point where the line of action of that body, that weight of the body acts, is where we are going to be having our center of gravity. I think you see, at that point, this point here, that's where we are going to be having our center of gravity. Then center of mass, this is the point at which the mass of the body is supposed to act. Now, this body here has a mass. You know that weight is given by mass times the gravitation. But now, the mass of this body, at this point, we also consider that the mass, the center of mass, is where the whole mass of this body, its mass is going to be acting at that point. And that's what we call the center of mass. But the center of gravity, through the line of action, in most cases, in some cases, not most, in some cases, the center of mass and the center of gravity may be at the same point, but not in all cases, in some cases. Okay, the center of gravity and center of mass coincide in uniform gravitation field, as I've told you there. Then the uniform body, this is the body with the uniform density, i.e. its weight acts in the middle, and so the center of gravity, like this. Now this one is a uniform body. Its center of gravity is going to act in the middle of that. So whenever that happens, even if it's a rod, even if I have this rod, when this rod is uniform, its center of gravity is always acting in the middle. I think you see it's balanced on both sides. So this one is a uniform body, as we saw in uniform rods. Now this is a uniform lamina. This one we call it a lamina. Okay. Center of gravity and center of mass are different due to the fact that gravitational force vary from one place to another. I think you know, depending on the planets and even on Earth, center of gravity in some places very, very different from other places. Okay, then so that's why we say that in some cases they differ, the center of mass and then the center of gravity. Because if the center of gravity changes, if gravity changes, it means that the center of gravity is going to also be affected. But this is so common in bigger bodies, but for small bodies, that change in center of gravity is negligible, and some people don't consider it, and so they neglect it in small bodies, but in big bodies, the case is different. Center of gravity, I thought this is how we abbreviate the center of gravity. Locate a particle is taken to be as a process of locating its center of gravity. So, where the center of gravity, where a particle is, it means that we can easily locate its center of gravity, then we have located that particle where it is. So, since the weight of the body acts vertically downwards, then we can always apply the moments to locate the center of gravity. So, you know, if I have a mass, always the weight, we say the weight is equal to mass times B. US, the gravitational force there. Then the weight is going to always act vertically downwards. Then there is a note here. Moments caused by a single mass M is always the same as moments caused by separate masses M1, M2, M3 up to Mn from N. So if I have this body, I'm separated into 4 parts. The moments caused by this body as a whole is equal to the moments caused by separating bodies from this same thing. That's the point there. So consider masses M1, M2, M3 located at points the center of mass, x bar, y bar. Now the center of mass for the whole mass. And immediately by taking moments about the coordinate axis we mean either the y-axis or the x-axis. If m is equal to the sum of that, so we adjust these ones are just small portions from the big mass. So you note that if I multiply by d in this side, I have d also that side, and already you see that these ones are going to be giving me weight. So the weight of this is going to be equal to the sum of the whole of these weights. So remember, if I get this and divide it into 4 parts, when I get the weights of those separate, it's going to be equal to the weight of one. You know that our mg is equal to the weight. So it's going to be equal to the weight of all those things there. Now, if I put them on the coordinate axis, the x-axis and the y-axis, now I'm assuming this is m2, this is one mass, one mass, one mass, one mass. Now, assuming that the center of gravity of the whole mass, this one, is here, it means that now, if we take moments for this about the x and y axis, it's going to be equal to the same moment. The moments of that is going to be equal to the sum of moments of these masses there. So, what I mean here, if this mass is here, of course, it's going to be having a weight, which we said we get the mass times b. The same here. Now this is the big body, this is the body. Now these ones are the separate, the 4 parts we are talking about, the 3 parts we are talking about. Of course, they are going to be having weight. I think this is acting vertically downwards, even this weight, even this one. Mn means the last separate mass we divided. Now, here you note, I need it for 3. From here up to here, the vertical distance is what we've covered. Then from here up to here, the horizontal distance is the x component. The vertical distance from here up to here is the y coordinate. The horizontal is the x coordinate. And so this is the same case. Even to this side, just use these two to so that the diagram is not so congested without of. Now, if you take moments at the y-axis means what? We said, remember in moments, of course we covered that topic and the videos are there in the playlists for moments. Okay, we said to get moments, you get the weight or you get the force times the perpendicular distance from where you're taking moments from. So now, we take moments about the y-axis. So now what I'm going to do, I'm going to consider first of all the mass of the whole thing, the body. Then its perpendicular distance, because I'm taking from the y-axis, the perpendicular weight is acting downwards. So its perpendicular distance from here up to here, we say it's going to be, because the weight is vertical, its perpendicular distance has to be horizontal. So meaning from here, its perpendicular distance is going to be x bar. That's why here I'm adding now the weight mg times x bar. So we are there. Now we say that the moments, now we are taking them clockwise. So meaning the moments produced by this whole mass clockwise is going to be equal to the sum of moments produced by the separate masses from this m clockwise. Don't confuse it with the principal of moments. No. Here we are saying the clockwise moments by the whole particle is going to be equal to the sum of clockwise moments by the separate particles from that whole mass. That's the point there. So this is the idea doing. We are getting now, let me use 1 from here and here. So this weight is acting downwards. Its perpendicular distance is going to be from here up to here, and it's this x, because we need, if the weight is vertical, then the perpendicular distance has to be horizontal, because it should be perpendicular. That's why I'm getting the weight times the horizontal. The weight times the horizontal for mass 2, then the weight times the horizontal for mass n. And so you can see that we say the whole of this, when we sum all these ones, we are getting our then times the x components there. This is going to be the x bar. Now this is where, this is the x component for that big mass. If we divide through by this, and we take the the other side, that's what we are having. This is a product of these two things there. And so if you take now about the y-axis, you see, if you take about the x-axis, now it means that our weight is going to act still downwards. And now at the x-axis, because the weight, we are going to be considering now the horizontal distance, the horizontal distance from here up to here. It's going to be now the y coordinates, as you see. So this is now our weight, but the perpendicular distance from here up here is going to be the y, because the y there. So, and so the same idea, this MD is equal to here as you see it there. And if you divide through by this, that's what we have there. Basically, when you do that, then we are going to come to the point when they give us these coordinates, the ideal interpretation. This is what I've been talking about, and it's always there. So, see you in the next lesson.